Network address translation is a methodology of modifying network address information in Internet Protocol datagram packet headers while they are in transit across a traffic routing device for the purpose of remapping one IP address space into another. Network address translation was originally used to map every address of one address space to a corresponding address in another space, such as when an enterprise changed Internet service providers without having a facility to announce a public route to the network. Most often today, NAT is used in conjunction with IP masquerading, which is a technique that hides an entire IP address space, usually consisting of private network IP addresses, behind a single IP address in another, usually public address space. This mechanism is implemented in a routing device that uses stateful translation tables to map the hidden addresses into a single IP address and readdresses the outgoing Internet Protocol packets on exit so they appear to originate from the routing device. In the reverse communications path, responses are mapped back to the originating IP addresses using the rules stored in the translation tables. The translation table rules established in this fashion are flushed after a short period unless new traffic refreshes their state. The method enables communication through the router only when the conversation originates in the masqueraded network, since this establishes the translation tables. For example, a web browser in the masqueraded network can browse a website outside, but a web browser outside could not browse a website hosted within the masqueraded network. However, most NAT devices today allow the network administrator to configure translation table entries for permanent use. This feature is often referred to as static NAT, or port forwarding, and allows traffic originating in the outside network to reach designated hosts in the masqueraded network. Because of the popularity of this technique to conserve IPv4 address space, the term NAT has become virtually synonymous with the method of IP masquerading. As network address translation modifies the IP address information in packets, it has serious consequences on the quality of Internet connectivity and requires careful attention to the details of its implementation. NAT implementations vary widely in their specific behavior in various addressing cases and their effect on network traffic. The specifics of NAT behavior is not commonly documented by vendors of equipment containing implementations. Basic NAT, the simplest type of NAT, provides a one-to-one translation of IP addresses. RFC 2663 refers to this type of NAT as basic NAT, which is often also called a one-to-one NAT. In this type of NAT, only the IP addresses, IP header checksum and any higher-level checksums that include the IP address are changed. Basic NATs can be used to interconnect two IP networks that have incompatible addressing. It is common to hide an entire IP address space, usually consisting of private IP addresses, behind a single IP address in another, usually public address space. To avoid ambiguity in the handling of return packets, a one-to-many NAT must alter additional information such as TCP UDP port numbers in outgoing communications and must maintain a translation table so that return packets can be correctly addressed to the originating host. RFC 2663 uses the term network address and port translation for this type of NAT. Other names include port address translation, IP masquerading, NAT overload and many-to-one NAT. This is the most common type of NAT, and has become synonymous with the term NAT in common usage. As described, the method enables communication through the router only when the conversation originates in the masqueraded network, since this establishes the translation tables. For example, a web browser in the masqueraded network can browse a website outside, but a web browser outside could not browse a website hosted within the masqueraded network. However, most NAT devices today allow the network administrator to configure translation table entries for permanent use. This feature is often referred to as static NAT, or port forwarding, and allows traffic originating in the outside network to reach designated hosts in the masqueraded network. One-to-many NAT, the majority of NATs map multiple private hosts to one publicly exposed IP address. In a typical configuration, a local network uses one of the designated private IP address subnets. A router on that network has a private address in that address space. The router is also connected to the Internet with a public address assigned by an Internet service provider. As traffic passes from the local network to the Internet, the source address in each packet is translated on the fly from a private address to the public address. The router tracks basic data about each active connection. When a reply returns to the router, it uses the connection tracking data it stored during the outbound phase to determine the private address on the internal network to which to forward the reply. All datagram packets on IP networks have a source IP address and a destination IP address. Typically, packets passing from the private network to the public network will have their source address modified, while packets passing from the public network back to the private network will have their destination address modified. More complex configurations are also possible. To avoid ambiguity in how to translate return packets, further modifications to the packets are required. The vast bulk of Internet traffic is TCP and UDP packets, and for these protocols the port numbers are changed so that the combination of IP and port information on the return packet can be unambiguously mapped to the corresponding private address and port information. Protocols not based on TCP or UDP require other translation techniques. ICMP packets typically relate to an existing connection and need to be mapped using the same IP and port mappings as that connection. Methods of port translation. There are several ways of implementing network address and port translation. In some application protocols that use IP address information, the application running on a node in the masqueraded network needs to determine the external address of the NAT, that is, the address that its communication peers detect, and, furthermore, often needs to examine and categorize the type of mapping in use. Usually this is done because it is desired to set up a direct communications path between two clients, both of which are behind separate NATs. For this purpose, the simple traversal of UDP over NATs protocol was developed. It classified NAT implementation as full co-NAT, restricted co-NAT, port-restricted co-NAT or symmetric NAT and proposed a methodology for testing a device accordingly. However, these procedures have since been deprecated from standard status, as the methods have proven faulty and inadequate to correctly assess many devices. New methods have been standardized in RFC 5389 and the STAN acronym now represents the new title of the specification, Session Traversal Utilities for NAT. This terminology has been the source of much confusion, as it has proven inadequate at describing real-life NAT behavior. Many NAT implementations combine these types, and it is therefore better to refer to specific individual NAT behaviors instead of using the cone-symmetric terminology. Especially, most NAT translators combine symmetric NAT for outgoing connections with static port mapping, where incoming packets to the external address and port are redirected to a specific internal address and port. Some products can redirect packets to several internal hosts, for example to divide the load between a few servers. However, this introduces problems with more sophisticated communications that have many interconnected packets, and thus is rarely used. Type of NAT and NAT traversal. Role of port preservation for TCP. The NAT traversal problem arises when two peers behind distinct NAT try to communicate. One way to solve this problem is to use port forwarding, another way is to use various NAT traversal techniques. The most popular technique for TCP NAT traversal is TCP hole punching, which requires the NAT to follow the port preservation design for TCP, as explained below. Many NAT implementations follow the port preservation design for TCP. For a given outgoing TCP communication, they use the same values as internal and external port numbers. NAT port preservation for outgoing TCP connections is crucial for TCP NAT traversal, because as TCP requires that one port can only be used for one communication at a time, programs bind distinct TCP sockets to ephemeral ports for each TCP communication, rendering NAT port prediction impossible for TCP. On the other hand, for UDP, NATs do not need to have port preservation. Indeed, multiple UDP communications can occur on the same source port, and applications usually reuse the same UDP socket to send packets to distinct hosts. This makes port prediction straightforward, as it is the same source port for each packet. Furthermore, Port preservation in NAT for TCP allows P2P protocols to offer less complexity and less latency because there is no need to use a third party to discover the NAT port since the application itself already knows the NAT port. However, if two internal hosts attempt to communicate with the same external host using the same port number, the external port number used by the second host is chosen at random. Such NAT is sometimes perceived as restricted co-NAT and other times as symmetric NAT. Recent studies have shown that roughly 70% of clients in P2P networks employ some form of NAT. Implementation: establishing two-way communication. Every TCP and UDP packet contains a source IP address and source port number as well as a destination IP address and destination port number. The port address IP address pair forms a socket. In particular, the source port and source IP address form the source socket. For publicly accessible services such as web servers and mail servers, the port number is important. For example, port 80 connects to the web server software and port 25 to a mail server's SMTP daemon. The IP address of a public server is also important, similar in global uniqueness to a postal address or telephone number. Both IP address and port must be correctly known by all hosts wishing to successfully communicate. Private IP addresses as described in RFC 1918 are significant only on private networks where they are used, which is also true for host ports. Ports are unique endpoints of communication on a host, so a connection through the NAT device is maintained by the combined mapping of port and IP address. PAT resolves conflicts that would arise through two different hosts using the same source port number to establish unique connections at the same time. Telephone number extension analogy: a NAT device is similar to a phone system at an office that has one public telephone number and multiple extensions. Outbound phone calls made from the office all appear to come from the same telephone number. However, an incoming call that does not specify an extension cannot be transferred to an individual inside the office. In this scenario, the office is a private LAN, the main phone number is the public IP address, and the individual extensions are unique port numbers. Translation of the endpoint: with NAT, all communications sent to external hosts actually contain the external IP address and port information of the NAT device instead of internal host IPs or port numbers. When a computer on the private network sends an IPv4 packet to the external network, the NAT device replaces the internal IP address in the source field of the packet header with the external IP address of the NAT device. PAT may then assign the connection a port number from a pool of available ports, inserting this port number in the source port field, and forwards the packet to the external network. The NAT device then makes an entry in a translation table containing the internal IP address, original source port, and the translated source port. Subsequent packets from the same connection are translated to the same port number. The computer receiving a packet that has undergone NAT establishes a connection to the port and IP address specified in the altered packet, oblivious to the fact that the supplied address is being translated. A packet coming from the external network is mapped to a corresponding internal IP address and port number from the translation table, replacing the external IP address and port number in the incoming packet header. The packet is then forwarded over the inside network. Otherwise, if the destination port number of the incoming packet is not found in the translation table, the packet is dropped or rejected because the PAT device doesn't know where to send it. NAT only translates IP addresses and ports of its internal hosts, hiding the true endpoint of an internal host on a private network. Visibility of operation: NAT operation is typically transparent to both the internal and external hosts. Typically the internal host is aware of the true IP address and TCP or UDP port of the external host. Typically the NAT device may function as the default gateway for the internal host. However, the external host is only aware of the public IP address for the NAT device and the particular port being used to communicate on behalf of a specific internal host. NAT and TCP/UDP, pure NAT, operating on IP alone, may or may not correctly parse protocols that are totally concerned with IP information, such as ICMP, depending on whether the payload is interpreted by a host on the inside or outside of translation. As soon as the protocol stack is traversed, even with such basic protocols as TCP and UDP, the protocols will break unless NAT takes action beyond the network layer. IP packets have a checksum in each packet header, which provides error detection only for the header. IP datagrams may become fragmented, and it is necessary for a NAT to reassemble these fragments to allow correct recalculation of higher-level checksums and correct tracking of which packets belong to which connection. The major transport layer protocols, TCP and UDP, have a checksum that covers all the data they carry, as well as the TCP-UDP header, plus a pseudo-header that contains the source and destination IP addresses of the packet carrying the TCP-UDP header. For an originating NAT to pass TCP or UDP successfully, it must recompute the TCP-UDP header checksum based on the translated IP addresses, not the original ones, and put the checksum into the TCP-UDP header of the first packet of the fragmented set of packets. The receiving NAT must recompute the IP checksum on every packet it passes to the destination host, and also recognize and recompute the TCP-UDP header using the retranslated addresses and pseudo-header. This is not a completely solved problem. One solution is for the receiving NAT to reassemble the entire segment and then recompute a checksum calculated across all packets. The originating host may perform maximum transmission unit path discovery to determine the packet size that can be transmitted without fragmentation, and then set the don't fragment bit in the appropriate packet header field. DNAT, Destination Network Address Translation, is a technique for transparently changing the destination IP address of an en route packet and performing the inverse function for any replies. Any router situated between two endpoints can perform this transformation of the packet. DNAT is commonly used to publish a service located in a private network on a publicly accessible IP address. This use of DNAT is also called port forwarding, or DMZ, when used on an entire server, which becomes exposed to the WAN, becoming analogous to an undefended military demilitarized zone. SNAT. The meaning of the term SNAT varies by vendor. Many vendors have proprietary definitions for SNAT. Source NAT is the common expansion, as the counterpart of Destination NAT. Stateful NAT is used by Cisco systems, Static NAT is used by WatchGuard systems, Secure NAT is used by F5 networks and by Microsoft. Microsoft's Secure Network Address Translation is part of Microsoft's Internet Security and Acceleration Server and is an extension to the NAT driver built into Microsoft Windows Server. It provides connection tracking and filtering for the additional network connections needed for the FTP, ICMP, H323, and PPTP protocols, as well as the ability to configure a transparent HTTP proxy server. Dynamic Network Address Translation, Dynamic NAT, just like Static NAT, is not common in smaller networks but is found within larger corporations with complex networks. The way Dynamic NAT differs from Static NAT is that where Static NAT provides a one-to-one internal to public static IP address mapping, Dynamic NAT doesn't make the mapping to the public IP address static and usually uses a group of available public IP addresses. Nat Loopback, also known as Nat hairpinning or Nat reflection, is a feature in many consumer routers which allows a user to connect to his/her own public IP address from inside the LAN network. This is especially useful when, for example, a website is hosted at that IP address. The following describes an example network: public address, 203.0.113.1, internal address of router, 192.168.1.1, address of the server, 192.168.1.2, address of a computer, 192.168.100.1. If a packet is sent to the public address by a computer at 192.168.100.1, the packet would normally be routed to the default gateway, unless an explicit route is set in the computer's routing tables. A router with the Nat Loopback feature detects that 203.0.113.1 is the address of its WAN interface, and treats the packet as if coming from that interface. It decides based on DNAT rules on the destination for the packet. For example, If the data was sent to port 80 and there is a DNAT rule for port 80 directed to 192.168.1.2, then the host at that address will receive the packet. If no applicable DNAT rules are available, the router's firewall drops the packet. An ICMP destination and reachable reply may be sent. If any DNAT rules were present, address translation is still in effect. The router still rewrites the source IP address in the packet. The computer sends the packet as coming from 192.168.100.1, but the server receives it as coming from 203.0.113.1. When the server replies, the process is identical as for an external sender. Thus, two-way communication is possible between hosts inside the LAN network via their public IP address. Nat Loopback is especially useful when the server hosts a domain name that resolves to a public address. When the router does not perform Nat Loopback, any connection attempts to that IP address fail. Security. Nat Loopback is sometimes rumored to be a security issue and may be said to provide land attacks, but this is incorrect. No technical grounds are known for the security accusations. In the event of a land attack, the router with Nat Loopback would reply to itself when a packet has the source address set to itself. However, Nat Loopback makes the router look up the destination address and port in its port forwarding rules table. When none is found, the packet is discarded and no error response is sent back. If this were the case, then the code making that response should make sure that it's not sending it to itself. The same would happen with any other packet originating from the LAN or WAN, so a land attack is unrelated to Nat Loopback itself. NAT in IPv6, network address translation is not commonly used in IPv6 as one of its aims is to restore true host-to-host connectivity. Nat Loopback is not commonly needed. Although still possible, the large addressing space of IPv6 obviates the need to conserve addresses and every device can be given a unique globally routable address. Nat Loopback, when implemented, works as in IPv4. Applications affected by NAT. Some application layer protocols send explicit network addresses within their application data. FTP in active mode, for example, uses separate connections for controlled traffic and for data traffic. When requesting a file transfer, the host making the request identifies the corresponding data connection by its network layer and transport layer addresses. If the host making the request lies behind a simple NAT firewall, the translation of the IP address and/or TCP port number makes the information received by the server invalid. The session initiation protocol controls many voice-over IP calls, and suffers the same problem. SIP and SDP may use multiple ports to set up a connection and transmit voice stream via RTP. IP addresses and port numbers are encoded in the payload data and must be known prior to the traversal of NATs. Without special techniques, such as stun, NAT behavior is unpredictable and communications may fail. Application layer gateway software or hardware may correct these problems. An ALG software module running on a NAT firewall device updates any payload data made invalid by address translation. ALGs obviously need to understand the higher layer protocol that they need to fix, and so each protocol with this problem requires a separate ALG. For example, on many Linux systems, there are kernel modules called connection trackers which serve to implement ALGs. However, ALG does not work if the control channel is encrypted. Another possible solution to this problem is to use Nat Traversal techniques using protocols such as stun or ICE, or proprietary approaches in a session border controller. Nat Traversal is possible in both TCP and UDP-based applications, but the UDP-based technique is simpler, more widely understood, and more compatible with legacy NATs. In either case, the high-level protocol must be designed with Nat Traversal in mind, and it does not work reliably across symmetric NATs or other poorly behaved legacy NATs. Other possibilities are UPnP Internet Gateway Device Protocol, NatPMP, or Port Control Protocol, but these require the NAT device to implement that protocol. Most traditional client-server protocols, however, do not send Layer 3 contact information and therefore do not require any special treatment by NATs. In fact, avoiding NAT complications is practically a requirement when designing new higher-layer protocols today. NATs can also cause problems where IPsec encryption is applied and in cases where multiple devices such as SIP phones are located behind a NAT. Phones which encrypt their signaling with IPsec encapsulate the port information within an encrypted packet, meaning that NA/P/T devices cannot access and translate the port. In these cases the NA/P/T devices revert to simple NAT operation. This means that all traffic returning to the NAT is mapped onto one client, causing service to more than one client behind the NAT to fail. There are a couple of solutions to this problem. One is to use TLS, which operates at level 4 in the OSI reference model and therefore does not mask the port number. Another is to encapsulate the IPsec within UDP, the latter being the solution chosen by Tispan to achieve secure NAT traversal, or a NAT with IPsec pass-through support. Interactive connectivity establishment is a NAT traversal technique which does not rely on ALG support. The DNS protocol vulnerability announced by Dan Kaminsky on July 8, 2008 is indirectly affected by NAT port mapping. To avoid DNS server cache poisoning, it is highly desirable to not translate UDP source port numbers of outgoing DNS requests from a DNS server which is behind a firewall which implements NAT. The recommended workaround for the DNS vulnerability is to make all caching DNS servers use randomized UDP source ports. If the NAT function de-randomizes the UDP source ports, the DNS server becomes vulnerable. Port address translation. Port address translation allows many internal hosts to share a single external IP address. Users who do not require support for inbound connections do not consume public IP addresses. The primary purpose of IP masquerading NAT is that it has been a practical solution to the impending exhaustion of the IPv4 address space. Even large networks can be connected to the Internet with a single IP address. The more common arrangement is having computers that require end-to-end connectivity supplied with a routable IP address, while having others that do not provide services to outside users behind NAT with only a few IP addresses used to enable Internet access. Some have also called this exact feature a major drawback, since it delays the need for the implementation of IPv6. It is possible that its, NAT's, widespread use will significantly delay the need to deploy IPv6. It is probably safe to say that networks would be better off without NAT. Hosts behind NAT-enabled routers do not have end-to-end connectivity and cannot participate in some Internet protocols. Services that require the initiation of TCP connections from the outside network, or stateless protocols such as those using UDP, can be disrupted. Unless the NAT router makes a specific effort to support such protocols, incoming packets cannot reach their destination. Some protocols can accommodate one instance of NAT between participating hosts, sometimes with the assistance of an application-level gateway, but fail when both systems are separated from the Internet by NAT. Use of NAT also complicates tunneling protocols such as IPsec because NAT modifies values in the headers which interfere with the integrity checks done by IPsec and other tunneling protocols. End-to-end connectivity has been a core principle of the Internet, supported for example by the Internet Architecture Board. Current Internet architectural documents observe that NAT is a violation of the end-to-end principle, but that NAT does have a valid role in careful design. There is considerably more concern with the use of IPv6 NAT, and many IPv6 architects believe IPv6 was intended to remove the need for NAT. Because of the short-lived nature of the stateful translation tables in NAT routers, devices on the internal network lose IP connectivity typically within a very short period of time unless they implement NAT keep-alive mechanisms by frequently accessing outside hosts. This dramatically shortens the power reserves on battery-operated handheld devices and has thwarted more widespread deployment of such IP-native Internet-enabled devices. Some Internet service providers, especially in India, Russia, parts of Asia and other developing regions, provide their customers only with local IP addresses, due to a limited number of external IP addresses allocated to those entities. Thus, These customers must access services external to the ISP's network through NAT. As a result, the customers cannot achieve true end-to-end connectivity, in violation of the core principles of the Internet as laid out by the Internet Architecture Board. Scalability, an implementation that only tracks ports, can be quickly depleted by internal applications that use multiple simultaneous connections. This problem can be mitigated by tracking the destination IP address in addition to the port, at the expense of implementation complexity and CPU memory resources of the translation device. Firewall complexity, because the internal addresses are all disguised behind one publicly accessible address, it is impossible for external hosts to initiate a connection to a particular internal host without special configuration on the firewall to forward connections to a particular port. Applications such as VoIP, video conferencing, and other peer-to-peer applications must use Nat Traversal techniques to function. IEEE reverse address and port translation allows a host whose real IP address is changing from time to remain reachable as a server via a fixed home IP address. In principle, this should allow setting up servers on DHCP-run networks. While not a perfect mobility solution, wrapped together with upcoming protocols like DHCP-DDNS, it may end up becoming another useful tool in the network admin's arsenal. Cisco-wrapped implementation is port address translation or NAT overloading, and maps multiple private IP addresses to a single public IP address. Multiple addresses can be mapped to a single address because each private address is tracked by a port number. PAT uses unique source port numbers on the inside global IP address to distinguish between translations. The port number are 16-bit integers. The total number of internal addresses that can be translated to one external address could theoretically be as high as 65,536 per IP address. Realistically, the number of ports that can be assigned a single IP address is around 4,000. PAT attempts to preserve the original source port. If this source port is already used, PAT assigns the first available port number starting from the beginning of the appropriate port group 0 to 511, 512 to 1023, or 1024 to 65,535. When there are no more ports available and there is more than one external IP address configured, PAT moves to the next IP address to try to allocate the original source port again. This process continues until it runs out of available ports and external IP addresses. Mapping of address and port is a Cisco proposal which combines A+P port address translation with tunneling of the IPv4 packets over an ISP provider's internal Ipv6 network. In effect, it is an stateless alternative to carrier-grade NAT and DS Lite that pushes the IPv4 IP address port translation function entirely into the existing customer premises equipment NAT implementation, thus avoiding the NAT444 unstatefulness problems of carrier-grade NAT, and also provides a transition mechanism for the deployment of native IPv6 at the same time with very little added complexity. Examples of NAT software: Internet connection sharing, Windows NAT plus DHCP since W98SE, Wingate, like ICS plus lots of control, Iptables, the Linux packet filter and NAT, UpFilter, Solaris, NetBSD, FreeBSD, XMac, NPF, the NetBSD packet filter, PF, the OpenBSD packet filter, NetFilter, Linux packet filter framework, see also. References. External links. Nat Traversal test and results, characterization of different TCP NATs, a Euro paper discussing the different types of NAT, anatomy, a look inside network address translators, a Euro Volume 7, Issue 3, September 2004, Jeff Tyson, How Stuff Works, How Network Address Translation Works, Routing with NAT, How NAT Works, a Euro Cisco Systems.